And the maximum strength is developed by total deformation of the work strain hardened, the H16 condition. Do notice the absolute deformation of the grains. So H18 is the fully work hardened condition. This is the H18 fully work hardened condition, the maximum deformation of the grains. So we've gone from annealed to H12 to H14 to H16 to H18 with the corresponding increases, and H18 is the fully work hardened condition. Now, as the degree of work hardening increases, so the tensile strength and as the degree of work hardening increases, so does the tensile strength. But corresponding, the ductility reduces dramatically, much faster than the increase in tensile strength. So realistically, if you were going to press or bend form, only the H12 or H14 tempers have sufficient ductility to be worked. Or manipulated. The H16 and the H18 fully work hardened tempers have insufficient ductility for further mechanical working, even such a simple bending. So in designing products, it's essential there is sufficient ductility left to prevent brittle failure in service. Now, as we work harden, we compress the grains and plastically stretch or grow longitudinally in the direction of deformation, cold rolling. So we're inducing directionality. The directionality means that the mechanical properties, yield and tensile strength, will be slightly higher in the longitudinal direction than in the transverse, whilst ductility will be higher in the transverse direction. During work hardening of thick or heavy sections, the surface will be subjected to a much greater deformation than that experienced in the center. So we will see work hardening of the surfaces not being fully transmitted to the core. So the strain hardening gradient surface so there will be strain hardening gradients surface to core. So the surface might be H18, but the core may only be H14. Now, cold working traps the energy of the cold work within the deformed grains. When a heavily cold work metal is heated to about 50% of its melting temperature or higher, new grains start to form, and we term this process recrystallization. The process of new grains is called annealing. When we heat a heavily cold work metal above its recrystallization or higher temperature for a short period of time, we see the start of the recrystallization process, and we call this recovery. New grains start to seed, and we see a minor reduction on strength and increase in ductility. As we continue to heat for longer times above the recrystallization temperature, new grains start to grow, and the grains are said to be partially recrystallized. Accompanying the partial recrystallization, we experience a reduction in tensile strength and a corresponding increase in ductility. This means by controlling the amount of recrystallization, we can manipulate the amount of new grain growth and so control or set the decrease in strength and the increase in ductility. Thus, through controlling the degree of recrystallization of strain-hardened structures, we can control or adjust the strength and the ductility of non-heat treatable alloys 1, 3, or 5000 series. After holding for long periods of time above the recrystallization temperature, eventually all the strain-hardened grains will have been consumed and new grains will have formed. The microstructure is now fully annealed. Strength and ductility have been restored to their original conditions. Now, fully cold worked aluminium H1X condition lacks sufficient ductility for further working, such as pressing or annealing. So fully cold worked aluminium in the H1 condition have insufficient ductility and they risk brittle failure in service in components subjected to elastic movement, such as in suspension or in bridges. Now, aluminium in the H1 strain hardened conditions exhibit high elastic spring back, so are difficult to control. And fully cold worked aluminium in the H1 condition is not firmly stable if subjected to elevated temperatures such as welded or paint curing, as it will start to recrystallize in a non-controlled manner. Now, partial annealing enables strain-hardened alloys to be reduced in strength to the desired strength and ductility levels. Partial annealing gives thermal stability, preventing the aluminium recrystallizing in a non-controlled manner. Thus, on exposure for short periods of elevated temperatures, the annealed strength and ductility will not change. So partial annealing of the strain-hardened conditions allows the strength and ductility of non-heat treatable alloys 1, 3, and 5000 series to be tailored to the required levels. We can balance strength with increased ductility for forming. Partial annealing reduces the spring back on forming, so enables accurate forming. Partially annealed aluminium is firmly more stable, so it will not recrystallize in an uncontrolled manner. The European standard has designated the temper H2X to indicate strain hardened and partially annealed tempers. So the H2 says this is cold worked and partially annealed, and the second digit after the H2 indicates the degree of partial annealing. So H28 is fully strain hardened, partially annealed, fully hard, maximum strength, minimum ductility. H26 says this is strain hardened and partially annealed to a 3/4 hard condition. H24 says this is strain hardened and partially annealed half hard, a balanced strength with ductility. And H22 says this is strain hardened, partially annealed quarter hard. Let's see what this actually means to us in terms of strength. As before, we're plotting strength and ductility against annealing. In the fully work or strain hardened condition, the H28 is fully hard aluminium, has high strength but no ductility. It is brittle and will fail on manipulation or pressing. If we heat the cold worked aluminium to about 50% of its melting temperature or higher, that is the recrystallization temperature, and hold on temperature for a short period of time, new grains start to grow. This is the H26 strain hardened, partially annealed, quarter hard condition. We have seeded the growth of new grains, so started the recrystallization process. Accompanying the start of the recrystallization, we see a slight induction in strength and a corresponding increase in ductility. As we continue to heat for longer times above the recrystallization temperature, new grains start to grow. Accompanying the partial recrystallization, we experience a increase in ductility and a decrease in strength. This is the H24 strain hardened, partially annealed, half hard equivalent condition. This means by controlling the amount of recrystallization, we can manipulate the amount of new grain growth and so set the decrease in strength and the increase in ductility. Thus, through controlling the degree of recrystallization and strain hardened structures, we can control or adjust the strength and ductility. The strain hardened cold work structure is said to be partially recrystallized. The H24 half hard temper is a balance between strength and ductility. As we continue for very long, as we continue to heat for very long times above the recrystallization temperature, the rate of recrystallization, that is the growth of the new grains, becomes significant. The significant growth in new grains results in the H22 condition, partially annealed, quarter hard state, with large reduction in strength but greatly increased ductility. If we're intending to heavily manipulate, bend, or form the aluminium, then we need to use it in the H24 or 22 tempers. After a prolonged period of recrystallization above the recrystallization temperature, all new grains have grown. The structure is said to be fully annealed, and the strength and ductility are returned to their original levels. Minimum strength and maximum ductility, so highly formable. I trust you have now learned how to develop the properties of non-heat treatable alloys. Please see further reading. Thank you very much.